kind of, it's, before I show it to you, have you guys putting it in your measurements. So I hope you remember what we talked about last in this class, because so far in this part we've talked about coming up with, or the previous part, we talked about coming up with how much a molecule weighs. Pretty good. What's the units of molecular weight? AMU. Very good. Okay, so you come up with how much a molecule weighs, and then that actually, that same number is its molar mass. What are the units for molar mass? Grams per mole. Yep, molar mass. Very good, but it's the same number. Same number, but it's different units. So we're going to pick up where we left off. We're dealing with chloroform, which actually, I don't see any metals there. Remember, we've been talking about two types of compounds, molecular compounds and ionic compounds. If there's no metal in it, like there isn't here, I know there's no metal because I can do a jag like this, and I find the carbon here, non-metal, I find the chlorine here, non-metal, and for this purposes, hydrogen is also non-metal, so it's a molecular compound. So we're kind of supposed to find out how many moles there are in this grams of the compound. Now this should hopefully ring a bell because in units, this is unit 2. In unit 1 in here, we did the same sort of problem for elements, and now we're doing it for compounds. So, the first thing we're going to do is knock out the molar mass. Okay? So, what do we need to use? What tool do we have hanging on the wall? Periodic table. So, I'll kind of show you. This is the abbreviated way. So there's one carbon times 12.01 plus there's one hydrogen. The decimal number for hydrogen is 1.008. And then there are 3 chlorines. Chlorine's pretty heavy. So 3 times 35.45. And if that's a molar mass, what did you say my units are? Grams per mole, exactly. Now, I've been kind of harping on, you cannot use that just straight up like that. I would think of it as 119.37 G for grams over 1 mole. Because if I do that, then I know it's like my conversion factor. So the numbers on the previous slide, what number would I usually start with? Work this problem. 1.28. Yep. It'd be the mass, it'd be the 1.28 grams. Yep, over 1. So I'm going to ask you first if I'm going to use that just like that. And my second one is I'm going to flip it. So how many people think I'm going to use it just like that? How many think I'm going to flip it? I agree. So write down that number. So I've already done this in my calculator, but how many sig figs do I need to round it to? 3. Very good. So I flipped it. So my next term is 1 mole over 119.37 grams. And we've had this conversation. If you're dealing with only one compound, which we are, you don't have to put CHCl3. You guys told me 3 sig figs. I'm digging it. Just though remember that when I write down 3 sig figs, of course, this is just kind of to emphasize the decimal. This 0 is not significant. The 1 is significant, and and the 7 is significant. And I like to kind of think as the 0 between the 1 and the 7 is also significant. So you told me 3 sig figs, and there's 3 sig figs. Okay, so that was what, a grams to moles for compounds. Do another one. Here we go. Different compound. Now I see a number with moles, so that must be what I'm going to start with. That's going to be my first term, 0.4444 moles over 1. I'm going to use the molar mass of this compound. So we're going to use the periodic table, knock out the molar mass of CH4. I'm going to take 1 times 12.01 plus 4 times 1.008. And that gives me a molar mass of 16.04, and units of molar mass, you told me, were grams per mole. So to be more explicit what that really means, if I can use in a problem, 16.04 grams of this compound per 1 mole of this compound. So what's my first term going to be? Yep, 0.4444 mole. Yep. So how many people think I'm going to use it just like that? Can't trick you guys. Yes, I'm going to use it just like that. And using it just like that, now my units of moles cancel. So how many sig figs? 4. I'm liking 4. So you plug this into your calculator, you're looking at 7.129 grams. Now, just to kind of put perspective, why do we care about moles? Why can't we just do grams in just a minute, in chemistry? Did you get a different number?
Yeah.
I don't have my calculator, but it's possible. What'd you get?
7.1281.
Oh, okay. So that's quite possible. So 7.128, and the next number is 1?
Mm-hmm.
Okay. I will definitely concede that. What I started to say was, sorry, you're fine, thanks. Thank you. What I started to say is grams is awesome, but what we really care about is the number of molecules, the number of atoms, the number, and that goes back to moles. Grams is great, but moles is even better. All right. So I'm gonna mix it up just a little bit. I'm gonna add on to that sort of problem. If you read this a few times, there's a difference in this problem. What's the difference in this problem?
You're not finding the moles of the complete compound, you're finding the moles of bromine.
Yep, we're not finding the moles of complete compound. We're just finding the moles of bromine atoms. Moles of bromine atoms, exactly. Moles of bromine atoms. So in order to kind of show where we can go with this, so for instance, well, this is like a problem we did a little bit ago. I can go from grams of CBr4 to moles of CBr4 using the molar mass of CBr4. No problem, we just did that. But in order to kind of finish off this, we need to recognize that because we have the formula of the compound, we have 5 atoms stuck together, 1 carbon and 4 bromine atoms in that one molecule. And I know I can call it a molecule instead of formula unit because those are all nonmetals, carbon and bromine. It's a molecular compound, 1 molecule, we have 1 carbon and 4 bromine atoms. Well, if we scale it up, a mole is a number. So if we scale it up, in 1 mole of molecules, I have 4 moles of bromine atoms and 1 mole of carbon atoms. I got that just from the formula. That's it. So do you see where we can actually kind of see some equalities here? So I can come up with a nice equality. If I get to moles of CBr4 molecules, I can then get to moles of bromine atoms. This way. In 1 mole of molecules, I will have 4 moles of bromine atoms because of this 4 here. Okay? 1 mole of the molecules, we have 4 moles of the bromine atoms. Can split it up. Well, that little ratio right there, actually, you're going to see it when we knock out this problem. The problem's going to start just like we did the other problems. We're going to go from grams of the compound to moles of the compound, and then we're going to stick this in. Once we have moles of the compound, we can go to moles of bromine atoms. So here we go. Using the periodic table, we're going to take 1 times 12.01 for carbon, plus 4 times 79.90 for bromine, even heavier than chlorine. So that gives us a whopping molar mass of 331.61 grams of the compound per 1 mole of the compound. Actually, check this out. This time I'm gonna actually go CBr4. CBr4. I've talked in here about being explicit. Explicit just means as descriptive as possible. And this is one of those cases where probably going to work with top. So here we go. So what's my first term going to be? A few slides ago.
1.92.
Yep. 1.92 grams. And in this case, notice I am explicit. 1.92 grams of CBr4. And you might, I get this a lot sometimes. Students will say, like, how do I know when I need to be explicit? And how do I know when I can just roll with it? Like, I don't have to say what compound because there's only one compound. My answer is when you do enough problems. The other answer is if you don't know, you should be as descriptive as possible. Okay, so what's my next term going to be if I want to go to moles of CBr4? Yep, I'm hearing it. I'm going to use the flipped version of that, right? Very good. 1 mole of CBr4 over that 361.61 grams of CBr4. Perfect. Now, grams will cancel. Grams, specifically grams of CBr4 cancel. And I have moles of CBr4. Now what do I put in?
The last of.
Well, my goal is to get, I'm at moles of CBr4. How do I get moles of bromine atoms? Yep, a few slides ago, we came up with this. There, in 1 mole of CBr4, there are 4 moles of bromine atoms. And that's it. Now our moles of CBr4 molecules cancel. We have moles of Br atoms. Any questions about that last step? That just came from the formula. So how many sig figs? I hear 3. I'm liking 3 actually. It is 3 because we have 3 significant figures here, 5 here, and there's actually no uncertainty. That's exact. There's no uncertainty, so we'll go with 3 sig figs. So this is what I get. Is this what you got? 0.0232? Okay. 0.0232, and units would be those moles of cute little bromine atoms that we were after. When you see a mole, you should remember that a mole is, 6.022 times 10 to the 23rd. So lest you think that's a small number, that's not a small number of atoms, individual atoms. Okay. All right. So here's my little hint to make sure that you're explicit or descriptive where you need to be. And again, when in doubt, be descriptive. So, dun dun dun, all the homework due Thursday. And on to part 3. So I'm hoping I'm a little bit, not under the gun. Oh yeah. Lab. This is your lab sheet that I handed out, and I think it's available on Canvas. I will double check. So many times. So here, so what lab are we doing next week?
6.
It's right after you do the exam.
Yeah. Experiment 7. I don't know how to say that.
Stoichiometry. Experiment 7. That's my point. This is our roadmap. The experiment 7 is what we're doing. So make sure you do pre-lab for experiment 7. So there are experiments in there that we don't do. Okay? So I don't necessarily skip around, but I reserve the right. I never know if I want to pull something else in. We're doing 7. What I started to say is I'm trying to get to part, let's see, this is 3, 4, part 5, when we talk about equations, a little bit balancing and trigonometry portions.
So in our lab notebooks, right after experiment 3, we can write experiment 7.
Right, exactly. In your lab notebooks, right after experiment 3, you're going to write experiment 7. Yep. And what I usually do, this is my thing, I actually see the hole, so I stick this up by my desk. I usually go along the side and I'll superimpose another number that says, this is the first one, this is the second one, this is the third one, the fourth, the fifth, the sixth, the seventh. So I usually kind of do that along the side. If you do that, then you'll kind of match up in the grade book what is what. But here, those are the ones we're doing. So I'm hoping to get through these parts. I like this subject. We'll see what you think. All right, so, dun, dun, dun. If you want to put, I don't know how you guys do this, but if you want to put a star next to this sort of problem, you can do it like when we do the problem, but I promise you guys will have this sort of problem. And actually, this is almost not a problem to me, this is like a by definition. It's not really a problem. Like if you were to take water, what this problem does is basically water is H2O. You would say for every water molecule, what weight percent is hydrogen, what weight percent is oxygen. It's a very practical problem, okay? So that's what it is when we talk about percent elemental composition. We use the formula to knock out how much percent weight is brought by each element. So we're gonna pick on acetone. The formula for acetone's got 3 carbons, 6 hydrogens, and 1 oxygen. And actually, those all lie to the right of the JAG, so those are nonmetals. Remember, hydrogen's a nonmetal, oxygen and carbon nonmetal. This is a molecule. We're going to knock it out. So there's different ways to do this. For sure, you know, on your exam for this problem, you're going to have to show all of your work. And now you know for doing your alpha homework, if you want to get credit, you're going to show your work too. Okay, so I mentioned there's different ways to do it. In working chemistry problems, sometimes it's really helpful to come up with, to define your basis, like what you're going to sink your teeth into. And for working it this way, we're going to sink our teeth into 1 mole of the compound. So let's knock out the molar mass of acetone. So we take 3 times 12.01 plus 6 times 1.008 for the hydrogen. And there's only 1 oxygen, so plus 1 times 16.00. So the molar mass for acetone, you're looking at 58.08 grams per mole. And our basis is going to be 1 mole. So what mass do we have of acetone if we have 1 mole?
Say that again?
What mass of acetone do we have if we have 1 mole of acetone? 58.08 grams, exactly. And so we can kind of divvy up which element gives that 58.08 grams looking like this. So, with regard to that whole mass of 58.08 grams, carbon is bringing this amount. Now, what is this amount? This carbon is bringing 3 times 12.01 grams. How much is hydrogen bringing? 6 times 1.008 grams. How much is oxygen bringing? 1 times 16.00 grams. So we're getting close. We just basically took that 58.08 grams and we said, where's it coming from? Well, carbon, hydrogen, oxygen. That's where it's coming from, and that's the relative amounts. The last step in working this problem is kind of like a mixture. You guys remember when we did mixtures? We took the mass of the component and we divided by the total mass. On the next slide, what you're going to see is the mass of each of these elements individually divided by the total mass. So it looks like this.
Okay.
Yeah, so for carbon, in the numerator, the mass of carbon we said is 3 times 12.01 grams. The total mass of 1 mole of molecules is at 58.08 grams. And we know to get it to parts per 100, we take it times 100%. How many sig figs should we go with? 4. 4 is the right answer. Very good. So when I did the math, I got 62.04, and units would be percent. 62.04%. We take on the same pattern with hydrogen and oxygen. So hydrogen looks like this. We said for hydrogen, it's that 6 times 1.008 grams divided by that 58.08 grams times 100 to get it in parts per 100. 4 sig figs again, that's right. So 10.41% hydrogen. Same pattern with oxygen. We only had 1 oxygen atom times that 16.00 grams divided by the mass of the total mixture, 58.08 grams of acetone, times 100 to get it parts per 100. It's like 4 sig figs again. And you're looking at 27.55%. The next slide, it actually addresses this, just off the top of your head. We have 3 components, those are the 3%. What should they add up to be? 100%. It should add up to be 100%. Yes, ma'am? I think that's okay with that.
I just want to make sure it's okay for me to do it.
Yeah, she's double checking that she went ahead and multiplied these out and then put that number instead of the, but I think this gives more information. But that will be fine on a test. Okay, good question. So yeah, these actually added together equal 100% to 2 decimals. Now it's possible that you work this sort of problem and because of rounding, you're looking at maybe 99.95% or what's that? You could get 100.05%. It's just from rounding. You shouldn't get like 120% or something like that. Something's wrong. So you have one of these on your Unit 2 exam. There are a few twists to this though. Okay, so I'm like, oh, I hate that. But you probably have one straightforward and maybe one not straightforward. So in order to talk about kind of, I need to talk about this subject. So you guys are familiar with chemical formulas. So chemical formulas just they just show what atoms and how many are in that compound, whether that compound is a molecular compound or an ionic compound. Okay, chemical formulas. Well, there's 2 types of chemical formulas, broadly speaking. There are molecular formulas, and I like to tease that molecular formulas tell the real deal. We've talked, and I thought about putting it up here in our compare and contrast molecular compounds versus ionic compounds, but I don't think it's that big a deal.
So that's what we just did.
So molecular formulas, in contrast to,
Oh, that was first time, right?
yeah. I don't think we haven't entered it. The catch or the yang to molecular formulas is this one, empirical formulas. And I think, to me, I'm going to put empirical formulas, and I'm going to say possibly reduced. Possibly reduced, and I'll show you what I mean by reduced molecular formula. I don't know if I really want to say that, but it's kind of what I'm after. Possibly reduced. A molecular formula is the real deal. Empirical formulas say what elements are in that repeating unit, whether it's a molecule or an ionic compound, and they give the lowest whole number ratio of those elements. So you'll see what I mean by the reduction coming up. It's easier to show you than to. So we could look at butane. Butane, there's a lot of compounds out there that just have hydrogen or carbon and hydrogen in them. I just am amazed at that. It's a hydrocarbon. 4 carbons and 10 hydrogens for that one molecule. Now, we can divide both 4 and 10 by the number 2, and we could come up with another formula, a different formula. It's empirical formula. They both, the C4H10 and the C2H5, both give the same relative amount of carbon and hydrogen. The real deal of butane would be 4 carbons and 10 hydrogens, but the relative amount could be reduced to, say, C2H5. So some things can't be reduced. So the molecular formula of water, H2O, I can't divide 2 and 1 by a whole number and get another set of whole numbers. Okay, so it's molecular formula and it's empirical formula, the same thing. Hydrogen peroxide, my favorite one. Like the Santa Claus empirical formula. Oh, ho, ho. I like the last 2. Well, the last 2. Hydrazine, we looked at hydrazine. I can divide 2 and 4 by 2 and get 1 and 2. So the empirical formula is NH2. That's how all these things. The last 2 are hydrocarbons. I can reduce this to CH, can reduce acetylene to CH, and I can reduce benzene to CH. Simply put, all that means, we're gonna talk about combustion problems or analysis. If you burn it, acetylene and benzene, you're gonna get the same relative, or you can identify the same relative amounts of carbon and hydrogen in each of them. That's all that means. Okay, so there's a slight difference between molecular formula and empirical formula. Okay, so when we talked about molecular compounds and ionic compounds, remember ionic compounds had that kind of crazy crystalline lattice structure if they're in their solid state? And I said you have a hard time kind of picking which ion goes with which ion. So as it turns out, if you're writing the formula of an ionic compound, usually it's already reduced. That's my point. Ionic formulas are usually already empirical formulas. Okay, so why did I do all that? Well, we just did a problem when we came up with weight percents. For acetone, we came up with the relative weight of carbon, hydrogen, and oxygen in acetone. Okay? So the empirical formula of acetone, empirical formula of anything, gives relative amounts, but not in weight, it gives it in relative moles. Okay? So the percent elemental composition, relative mass, empirical formula, relative moles. Okay. So we did already for acetone, we came up with we knocked out a weight percent. That's pretty good. You can calculate percent elemental composition. If you're given any formula, whether it's the molecular formula or the empirical formula, I will tell you if you have two compounds that has the same empirical formula, they're going to have the same weight percent too. Sounds like you were okay with that. But now this is one that we're going to do. We are going to actually then backtrack. We're going to say if somebody goes ahead and tells you what weight percent you have for the elements in your compound, we're going to go from those weight percents to making a nice, neat, nice, tight little formula. We're going to go to the formula for that. And one of these will be on your test too. So I'm going to kind of I hope this is okay with you. I'm going to show you my slides, but I'm also going to do on the board how I would work this problem. Because this sort of problem to me just kind of screams like a little table. See if you guys see what I mean. So if you went to somewhere in your notes or on an extra piece of paper, this is how I would do it. I'm going to make different columns, and this first column is going to be the element I'm dealing with. And actually this approach is going to help you, this table approach will help you do other problems, other chemistry problems. All we're going to do is go from this weight percent. We must have a compound that has carbon, hydrogen, oxygen. There's a lot of those out there. And we have these weight percents, and we're going to come up with the formula. So in other words, our goal is CHO. Our goal is to say how many moles of carbon, how many moles of hydrogen, and how many moles of oxygen. Those little subscripts. We're coming up with the formula. So I knock out the elements, so I go carbon, hydrogen. I think that's how I did it. Oh my goodness, I can't spell. And oxygen. My little cheat sheet here. And so, here's the deal. I think I have this on the next slide. Do you see where I can unpack those percents? And if I take into consideration a basis of 100 grams, and usually if I'm trying to communicate a problem, up here in the corner, I'll say basis equals 100. I usually put 0.00 grams of compound, CPD. Do you see where those percentages turn into grams? Because they're parts per 100, grams per 100 grams. So then I'll usually put another column, I'll say mass of that particular element. And as you can see from the slide, mass of carbon, we just took its percent. And so you're looking at 53.3 grams of carbon. Mass of hydrogen, 11.2 grams. That came right from the percent of hydrogen. And the reason I like a table is because it organizes things and I don't have to keep writing what element I'm dealing with. Oxygen from its percent, you're looking at 35.6, 35.5, can't read my own handwriting, grams of oxygen. So you can see on this slide, and I'm going to make it into the form of a column, I'm going to call this moles. So how do I get from 53.3 grams of carbon to moles of carbon? Nope. Not Avogadro's number. Yep, I'm just going to use this on the periodic table. I'm going to find carbon, and for carbon, I got a 12.01, 2 decimals, and that's the grams per 1 mole of carbon. So actually, you can see on the slide here, I'm in this column, I'm going to say, I'm just going to be kind of lazy. I'm going to put that over 1. I'm going to say times, have to go 1 mole over 12.01 grams. And I don't have to say of carbon because I have that row labeled carbon. Okay. So you're looking at 4.44 moles. And again, I don't have to say moles of carbon because it's in that row. That's probably why I like this approach too. Okay, so we do a similar thing for hydrogen. 11.2 grams, I'll put it over 1. I can use the periodic table, and I know that 1 mole of hydrogen will weigh 1.008 grams. And rounding to 3 sig figs, you're looking at 1.11 moles. And I can do a similar thing for my oxygen. Use the periodic table, 1 mole of oxygen will weigh 16.00 grams. You divide that out, and you're looking at 3 sig figs, 2.22 moles. Yeah, and then it's time to eat chocolate. Because actually, and this might seem kind of silly, but I could take my carbon, hydrogen, and oxygen, and I could write 4.44 here, 1.11 here, 2.22 there. Now, I can't leave it that way because they need to be whole numbers. But you kind of get the idea.
Round.
Well, I'm going to fix it. And that's, again, why I like the table thing, because I'm going to clean it up. And this is my cleanup step. So the cleanup step goes like this. And sometimes you have to do 2 cleanup steps. I don't know if you need to do 3 cleanup steps. I'm going to make 1 more column. At the top of this column, I'm going to say, I'm going to literally divide by lowest. And what I mean by lowest, I'm going to divide by the lowest moles. So this column is divide by, this is my cleanup step, what, 1.11? Divide by 1.11. I'm going to actually, I know it sounds geeky, but if I'm working this problem to communicate it to myself, because that's your audience sometimes, I'm going to tell myself what I'm doing. So what is 4.44 divided by 1.11? 4. I'll go ahead and give it a 4.00. What's 1.11 divided by 1.11? 1. Yep. What's 2.22 divided by 1.11? 2.2. Yep.
This time you have 2 different answers.
Yeah, you're using 1.11.
Oh, thank you. Oh, wow, that makes a big difference. So we're not gonna.
1.11. Where are we getting this?
That's what I get.
That I didn't get math for.
Okay, thank you. Well, that changes everything. But if you showed your work, that would go a long way. So now which one do I divide by? What's my smallest?
2.
Yes, thank you. Divide by 2.22. That's the title of this one. So what's 4.44 divided by 2.22?
2.
Very good. What is 11.1 divided by 2.22? Like 5? So what we're looking for in this cleanup step are nice, neat, round numbers. And of course, what's 2.22 divided by 2.22? Thank you for pointing that out.
So, would we go to the nearest whole number?
So she asked, Megan asked, should we go to the nearest whole number? And actually, I'm going to kind of show you that it depends. You need to be very careful. I have a slide that says that when you're doing a problem like this, that the weight percent's very precise, and of course, those are very precise as we go from grams to moles. And so there's not a lot of wiggle. Be careful rounding. If it was like a 0.1 or 0.05 or something like that, I would round. I'm going to show you an example. If it's a 0.25, don't round. If it's a 0.3, don't round. If it's a 0.5, don't round. So it depends. There's one extra cleanup step we'll have to do. But if you buy this, then actually we have arrived. The formula is C2H5O1. That's it.
Would you need the one?
No, you don't need the one. But I put it just to emphasize it, but no. Yeah. So here's how my slides do it, but I like the table. My slides say, again, pick on the one that's smallest, and we said the one that's smallest was the moles of oxygen. So we can knock out the relative amount of carbon to oxygen by doing a division like we just did. It's similar to what we did. We'll come up with 2. Relatively speaking, for every 1 mole of oxygen, you have 2 moles of carbon. We do a similar thing for hydrogen. Relatively speaking, then, we take 11.1 by 2.22, you get that 5.00 moles of hydrogen for every 1 mole of oxygen. Okay, so I like the table. Again, this will actually get you down the road for another type of problem too. Okay? So we went from weight percent to the empirical formula. So I have a couple other, you guys get tired of hearing twists, okay? Okay, so empirical formula C2H5O1. All right, here's my caution. This was actually about the rounding, and I'm going to kind of show you why you don't round. So if it's, just be careful. And here's why. So for instance, if you came up with that, I call it the halvesies. Okay, if you came up with 1.5 somewhere in your cleanup, okay, actually, do you see where we could multiply both top and bottom by 2, and 1 times 2 is 2, and 1.5 times 2 is 3. So what we're going to see is I'm going to add a column. I'm going to multiply by 2 to clean that up. Watch out for thirdsies. Okay, so I could take both of these and multiply by 3, and 3 times 1 is 3, and 3 times 1.33 is 4. Okay, and actually this is my quarters. This could be for 1.25 or 1.75. If we multiply both numerator and denominator by 4, you get 4 here, and 4 times 1.25 is going to be 5. Another thing to watch out for, which is kind of related to your thirdsies, is 0.6s or 0.67s. Again, if I multiply top and bottom by 3, this cleans up to 3, obviously, and 3 times 2.67 actually is 8. So we're going to do a problem, and I'm going to add one more column. Okay. So the next problem I'd like to do is just a hydrocarbon, not with any oxygen, just hydrogen carbon. See if I can get this one right. So I'm going to erase, I'm going to start another table. I'm going to erase the oxygen row, and I'm going to erase the masses. But my first step is going to be to take those percentages, assume the basis is 100 grams, I'm going to turn those percentages into grams. Okay, so what you're going to see on my slide looks like this. So the grams of carbon from the percent is 82.7 grams. And we know that we can go ahead and knock that out into moles by using the periodic table. For carbon, 1 mole of carbon will weigh 12.01 grams. I got 6.89 moles. And then for hydrogen, from the weight percent, you're looking at 17.3 grams of hydrogen. We can use the periodic table. 1 mole of hydrogen will weigh 1.008 grams. You're looking at relative moles of 7.2 moles. And I told you the first step will be to divide by the smallest. So which is our smallest?
Carbon.
Yep, the carbon, exactly. So we're gonna divide by the carbon, which is 6.89. Okay, I'll make that my column. And of course, when I divide this, the first one's gonna be 1.00. And the next one, I get 2.50. If you take 17.2 moles divided by 6.89 moles, you get 2.50. So this was where we were talking, I said you cannot round up. So how can I clean this up? I'm digging it, multiply by 2. And why is that?
Because then you'll get 5 and 2.
Yep, because then this, if I take 2.50 times 2, I get 5. 1.0 times 2, I get 2.0, or 2. Yep. Any questions about that? So what would our formula be? Yep, C2H5. Yay!
So like, for
What's
the,
that?
when you do the formula, for like, so how do you know like what, okay, obviously carbon and hydrogen are usually, but how would you know like which element goes first?
Oh, which, for the rows? Or in the
like
formula?
that? Yeah.
I wouldn't, I would accept it like this.
It's the same.
Same thing.
Okay.
The communicative property of formulas.
Because like,
Traditionally, it's written like this,
on
but
the
I sure
homework,
wouldn't,
it was like
I
kind
would
of
give you a
like,
hard time.
yeah, on the homework
Yeah.
it was.
Yeah. But on the homework, they were picky? Okay. Okay, any questions about that? Sure.
This why did it divide by 6.89?
Because we looked at the moles, and this column's always gonna be divided by the smallest. So our choices were between these two, which is smallest.
The 6.87. Why did we
6.89 is smaller.
Oh, okay.
Yeah, so since we always just
Oh,
identify
it's not, yeah.
the smallest one. Yep.
Oh, I see.
Okay. Yay. Okay, well, there's one more type of problem, and we'll get to that on Wednesday. So we're gonna knock out 3. There's not a whole lot left for 3. There's homework, 3 homework to do on Thursday. Knock out Wednesday. And then there's a good chance I'll remind you, but we're gonna skip part 4 for now and go and come back to it. So we can get a little bit under your belt for your lab.